Well, hello, my good students. Welcome. Today's lesson is a big one. We're going to do some technical stuff. We're doing systems of equations, 3 different methods for solving them. Now, if I were doing this lesson in a classroom or so forth during a normal kind of a school year, I would probably take 3 days or more to do it, but we're going to try to get it done in one entire lesson. So it's technical. I have tried to make myself in the most relaxed area possible that I can do work. I'm even wearing my relaxed Hawaiian shirt. So you do the same. Get yourself in a place where you can work uninterrupted. Get some paper, some graph paper would help. The worksheet that I provide if you've got access to that. And let's get started. So you guys should be seeing my desktop now. All right, so activity 1, and this is still kind of review, but we're going someplace. Graph y is equal to negative x plus 4 on the Cartesian grid below. All right, so I'll do this in red. So in order to graph these, I want my y-intercept, which is 4, and my slope, which is negative 1. And so I come over here and go up 1, 2, 3, 4. I start right there, and then I go down 1, right 1, and down 1, right 1, and down 1, right 1, and so forth like that. And so I get this line then, and pardon me a second, in order to draw it, I got to kind of contort my body around. If you're working on a sheet of paper, you can probably just turn the paper, but I can't do that with an iPad. This must actually be how left-handed people feel when they try to write and stuff like that. But the world needs good left-handed people, so God bless them. That's probably how they feel. Oh my gosh. Okay, so I graphed it. Remember, the graph of an equation is the collection of all solution points. Now, the question is 1, 4 on the graph of the equation. Well, okay, let me take a look here. And if I go over 1, 2, 3, 4, I get 1. I get that point right there in blue. My answer is no. But then it says analyze algebraically. What? Well, I did it graphically. And if you remember that the graph of an equation is the collection of all solution points, that means if it's on the graph, it's a solution point. That means this x and y value here has to solve the equation. It has to solve this equation right here. Well, let's try it. Okay, so every time I use the equation, I'll write it down. So y is equal to negative x plus 4. And now let me substitute in my x and my y values. What's the y value? 4. And I'm asking, is it equal to, see the question mark? Is it equal to negative 1 plus 4? And so is 4 equal to 3? No. But see, I proved it then analytically. It's not a solution point. Okay, well, what about the next one? 3, 1. Is 3, 1 on the graph of the equation? Well, let's take a look here. 1, 2, 3, 1. Golly, I goofed that one up again, didn't I? All right, so I plotted the wrong point. I just realized that. You probably caught it. I was in a rush. I plotted the point 4, 1. But I wanted the point 1, 4, 1. 1, 2, 3, 4. That was that point. All right, so I make a mistake. But can you fix it? Are you satisfied now that that's the point 1, 4? I felt like a disturbance in the mathematical mind. Did anything need to change over there on the analytic side? Did I mess up the y and the x? No, I think I got that one right. Okay, I think we're back on track. Don't be afraid of math mistakes. Be afraid of not resolving them. Okay, that's why I want you guys to show your work, and why if you make a mistake, your job is to go back into your work and find where the mistake is made and then fix it. Simply erasing everything and starting all over may not help you all that much. You probably just make the same mistake you made the first time. But I think I've got it right there. And mathematics is not a matter of what I say it is. Mathematics is what it is. Just wait. And so I have to agree, I have to submit my belief to the truth of mathematics. And the truth of mathematics can be demonstrated. So anyway, back to part B now. Is 3, 1 on the graph of the equation? Well, I just checked it. It's this point right here. I don't need that anymore. This is the point 3, 1. Looks like it to me, But math is not about how it looks to me. Math is about certainty. So let's try this one now. The equation, what was it up there at the top? Y is equal to negative x plus 4. Okay, so this is the y value there, and that's the x value. So is 1 equal to, I don't know, I'm asking, negative 3 plus 4. Well, looky there. 1 is equal to 1. Yes. And we've proved it now analytically. Good. Okay. Now, next one. Graph y is equal to 2x or 2/3 x minus 1 on the Cartesian grid below. All right. So again, I'm going to take my y-intercept first, negative 1. And then I'm going to go up 2, right 3. So up 1, 2, right 1, 2, 3. Up 2, right 1, 2, 3. And then maybe down from the y-intercept, go down to left 3. And then I get this line right here. All you need is 2 points to graph it, but I want to be precise. And so it looks like that. Okay, is 3, 1 on the graph of this equation? Okay, let me double check. Let me pay attention this time. 3, so to the right, 1, 2, 3, and up 1. Well, they're in red. Well, it looks like it to me. Yes, but analyze it analytically. Okay, so I'll take the equation now. Y is equal to 2/3 x minus 1, and substitute in. This is my y value of 1 and x value of 3. So is 1 equal to, I don't know, I'm asking, 2/3 times 3 minus 1. And you should know that the whole number 3 is 3 over 1. And if I have a 3 on top and a 3 on the bottom, when I multiply, they cancel. So is 1 equal to 2 minus 1? Yes, it is. All right, so how about 6/3? Is 6/3 on the graph of the equation? I'll go back to red. 1, 2, 3, 4, 5, 6, 1, 2, 3. That point right there, that's 6/3. I still think it's yes, but let's find out. Analytically, what was the equation? Y is equal to 2/3 x minus 1. So recopy down. Y is equal to 2/3 x minus 1. And substitute in. This is my y, this is my x. Is 3 equal to, don't know, asking, 2/3 times 6 minus 1. All right, so 6 is over 1. That's going to cancel with that, leaving me a 1 down here and a 2 up there. So 2 times 2 is 3 equal to 4 minus 1. Woohoo! Also, yes. Good. Okay, making progress. That's review. Now, here's the question. Here's the question. Let's look at, can we look at both of these at the same time? I'm going to try to look at both at the same time. Okay, here's the question. I want to find a single point that will satisfy equation number 1 and at the same time equation number 2. I want one point that will solve both of them. What you think? Well, I kind of set you up, right? Isn't 3, 1 so on this equation, and then also 3, 1, like I gave them to you back to back, right? I set you up for that one. Oh yeah, the answer to the solution for both of them is 3, 1. But what if you weren't given options? What if I didn't tell you, hey, try this and hey, try that, and see if you get 2 that will work for both of them? What if it was just, blank? What would you do? Well, if the solution to an equation is the graph of the equation, and we've got 2 different equations, let's do 2 different graphs on the same coordinate grid. So activity number 3. Find a solution that will, and here's the key word, simultaneously. This is equation number 1, and this is equation number 2. Simultaneously means at the same time. Okay, so let's do, what color did I do in blue? Blue. I did the second one in blue. So let me do another one in blue again. So I'm going to go down, I'm going to graph this one, -1, and then up to right 3, and then up to and right 3. And then, so here's the graph from equation number 2. And I need to be precise. I need to be as precise as I can on this. Looks like that. And I did the other one in red, didn't I? Yeah. So -x plus 4. So 1, 2, 3, 4, and then down 1, right 1, down 1, right 1, down 1, right 1, and then down 1, right 1, and down 1, right 1. Oh, I gotta, golly, it gotta be awkward again. Oh man. Like that. Don't be sloppy. If you're sloppy, you're prone to make mistakes. Okay? Now, follow me on this. There's lots of points that solve the red equation. Let me switch to my little laser here. There's this point, and then there's this point, and 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 that point, and then this point, and that point, and that point, and that point. There's probably an infinite number. There are an infinite number of points that solve the red equation because it's got an infinite number of points on the graph. Okay? What about the blue one? Well, I got this point, and this point, and this point, and this point, and that point, and then this point, and this point, and this point, and this point, and this point. And there's a lot of different points. Where's the point that solves them both at the same time? You're looking for this location right there, which is the intersection. So the first technique in solving a system of linear equations is to look for the intersection point by graphing them. So the solution then is 3, 1. Okay? When x is 3, y is 1, it'll satisfy both of them. Nice, huh? Good. Sometimes two lines have trouble. Let me talk to you about this. I'm going to zoom in down here. If I had a line that looked like, I don't know, like this right here, and I graphed another equation, and that equation looked like, you know, this right here, where's the intersection point? There isn't one. Okay? What kind of lines are these? They're parallel lines. If you graph parallel lines, they don't have an intersection point. So what does that mean? There's no solution. There is no single point that solves both of them at the same time. Now, by looking at the equation, how can you figure out that they're parallel? Maybe even without graphing. You think about that. That's a great question. I'm going to leave that to you. Okay. There's another situation though that I have to talk about. Let me come in here. Let me use two colors I haven't done yet. Let me do green. Let's say I had a line that looked like that. And let's say I had another line, I'll use purple, that looked like that. Okay? Now they do intersect. There is a solution, but it's this location right here. But that doesn't fall on exactly on the coordinate grids. Like, how would you actually do that? Well, number one, you got to graph it really precisely. But number two, you're going to have to estimate. And there's no easy way around this. What is this point right here? Well, if I go back, here's my origin right there. If I go to the left, 1, 2, 3, 4, it looks like it's negative 4.2 to me, this point right there. But I'm just estimating. Okay, how high up is it? It looks like it's maybe a little higher up than it is sideways, so maybe 2.3. But I'm just estimating. In mathematics, a graph is good. A graph helps us understand the concept. But I would prefer an exact answer if I could. Mathematics gives you the possibility of exact values. So as it says right here, graphing's not the best method. So what other methods do we have? Okay, let's move on to the next page. Solve the system of equations by substitution. Now, if you took Algebra 1, you probably know how to do this, but let's talk about it. What? Substitution? Notice there's no graphing grid. I'm going to call this equation number 1, and I'm going to call this equation number 2. How do I find an x and a y value that solve both of those at the same time? Do I just guess and check until I find something? That might take me forever, especially if it's a fraction or a decimal. Good luck with that. Let me do something with number 1. I noticed that on number 1, the coefficient on x is 1. Now, I don't normally write 1 there. If you do, it's not technically wrong, but I will laugh and call you a newbie. So don't do that. But it's not technically wrong if you do. I'm going to solve that equation for x. I'm going to get x by itself. I'll do that by adding 7y to both sides. So plus 7y. These cancel. Those don't combine because they're not like terms. So if I come over here to the right, I'm going to get x is equal to 7y plus 11. Do you agree that that's still equation number 1? I mean, I did something legally allowed, right? Did the same thing to both sides? Okay, good. Now, if x is equal to 7y plus 11 in equation number 1, and I have to find the single x and y value that solves both of these at the same time, isn't the x value in equation number 2 the same thing as this x value in equation number 1? It has to be. Now let me tell you why. This is why it would be good for you to take a logic class. The very first rule of thought, the first rule of logic, or the first rule of thought is this. Number 1. Whatever is. You're like, wait a minute, what does that even say? It means that ideas have permanence, A-N-C-E, permanence of meaning. So, take for example the idea of something round. I'm looking around here. Do I have anything round? Oh, I'm looking around. That's interesting. Imagine like a sphere or something that's perfectly round, okay? You understand that idea. That idea is never changing. The concept of round is permanently round. You don't wake up tomorrow and find somehow that round has now become square. Now, physical things can go from round to square. If I had a ball of clay, I could make it into a round shape, and then I could change it into a squared shape. But square does not become round as an idea. In fact, something that is round cannot at the same time be both round and square at the same time and in the same sense. That's getting into another rule of logic. Okay, so we're talking about ideas. You don't wake up tomorrow and all of a sudden the universe has changed and 2 plus 3 is 7. No, 2 plus 3 is 5 and it will always be 5, okay? That's a permanent idea. Now we may change numbers in terms of physical things changing. We may even change meaning of the word. So when I say round in one sense, maybe I don't mean the same idea in another sense, like when I said I'm looking around. Maybe it was kind of round, but like words can have multiple meanings. I'm not talking about words meaning the same thing always. I'm talking about the idea being permanent. Okay? So here's the thing. If we say that x is equal to 7y plus 11 in this particular situation, it has to be that every place else, okay, including in equation number 2. So what we're going to do is we're going to take equation number 2, and I'll do it in red, and we're going to say 5 times the x value plus 4y equals negative 23. And I'm going to replace it with what it must be equal to, 7y plus 11. What is x? X is 7y plus 11. Waha! Okay, now what? Now the x is gone. I can just solve it for y. So multiply in. This becomes 35y plus 55 plus 4y equals negative 23. Keep on going. 35y plus 4y, that's 39y. Can I at the same time Subtract 55 from the left and minus 55 from the right. I hope you can track that. That equals then, if I did the math right, negative 78. Okay, and then if I divide by 39 over here and divide by 39 over there, I don't have that memorized. I'm going to reach for my machine. The answer is going to be negative. Oh, what do I get here? 78 divided by 39. I think that 2. So y is negative 2. Nice. Okay. I've substituted x in the second equation with what it had to be equal to from the first equation. Okay. Now, let me go back in and solve it then for x, because I'm not finished yet. Let me come back over here. Now, you could plug it into this equation, or you could plug it into equation number 2, but I've already got this equation right here, the modified one, solved for x, so it's easier just to do it in that one. But look, let's be honest, like I said, if y is negative 2 here on this one, it's negative 2 everywhere else in the entire problem. So it doesn't matter where you put it. You're bound to get the same x value if you do the math right. So back up now to x. And so x then is equal to, I'm doing this right here, 7 times y. But y we said was negative 2. Got to have parentheses, otherwise it looks like subtraction. Plus 11. So x then is equal to negative 14 plus 11. I get x is equal to, what's that, negative 3? There we go. Now I'm finished. So that is solving the systems by substitution. Here's my final answer, negative 3, negative 2. Put parentheses around them because they're an ordered pair. Box that. That's my final answer. Okay? That's solving by substitution. You got to replace the variable in one of the equations with its equivalent expression that you get from the other one. Okay? Now, let's do this one. Solve the system by substitution, check by graphing. Okay, I'm going to call this equation number 1 and this equation number 2. And look, equation number 2 is already solved for y. It's y is 2x minus 3. I don't even have to do any algebra with that one. So let me just come straight across and substitute. I'm going to replace y with the expression. So it's 2x minus the y that I'm going to get from down below equals negative 2. And I'll take this 2x minus 3 and plug it in right there. 2x minus 3. And now I will simplify. 2x minus 6 equals negative 2. Okay, collect my like terms. Wait a minute. They cancel out. Positive 2x minus 2x is 0. Okay, so then minus 6 is equal to negative 2. No, it should be plus 6. I got to distribute that negative. Plus 6. There we go. But there's no variable. Is this a true statement? No. This is false. What just happened here? Did I make a mistake? I don't think that I did. Well, it says check by graphing, so let me try that. I'll do the second equation in red because that one's easy. Y is equal to 2x minus 3. Okay, all right, come over here. Minus 3 then for my y-intercept, and I'm going to go up 2, right 1. Slope is 2, up 2, right 1, up 2, right 1. I get this graph. Looks like this right here. Okay. It's really kind of ugly. I'm embarrassed, but I'm in a hurry. Okay, so now let me do the other one in blue. Y is equal to, 2x minus y is equal to negative 2. I could solve this one for y, but let me just do like a table of values. Let me just do intercepts, x and y. So if x is 0, that gives me negative y is equal to negative 2. That means y is equal to positive 2. There's one of the points. And then when y is 0, it kills this whole thing, and I get 2x is equal to negative 2 divided by, that would be negative 1. So here's my two intercepts, if you remember how to do that. 0 and 2, which would be right there, and then negative 1 and 0, which would be right here. And so I get this line right there. And draw it neatly. Obviously, if you're on paper, you can use a straight edge. Straight edges don't work on an iPad all that well. Oh, wait a minute. What kind of lines are these? Parallel. No solution. See, I didn't do anything wrong. When the variable drops out and you have a false statement that remains, you have no solution. There is no place where those things will intersect. That's what that means when it happens analytically. Okay. Now, there's an alternate situation. An alternate situation would be like you did your variables and you had like a 2x minus a 2x plus 5 is equal to 5. And then these will cancel, and then you have 5 is equal to 5, but no variable. Well, this is a true statement. Okay, what does that mean? That means you actually have the same line. One of the lines would be the red one, and then another line would be then a blue one. It's the same thing, and you would then say you have an infinitely many solutions. Infinitely many. Now, not everything will work. Obviously, a point way down here will not work. Not everything will solve it, but there are an infinite number of points to do. Okay, so when you do analytic stuff and your variable drops out and a false statement remains though, it's no solution. Okay, so now this one, activity number 6, like a story question. I'm not going to totally solve this one, but I'll walk you through how to set it up. John has a total of 9 stamps, which cost 25 cents and 2-cent stamps, which consist of 25-cent and 2-cent stamps. His stamps have a value of $1.10. How many of each stamp does he have? Woohoo! I see 2 relationships here. He has a total of 9 stamps. That's how many stamps. And he also has a total value of $1.10. And so there's a different situation there. That's how much, come on, M, value the stamps have. Okay? Now he's got 2 different kinds, so that means I need to have 2 different variables. Can I call X the number of 25-cent stamps and then Y the number of 2-cent stamps? I'll probably better write that down. X is the number, not hashtag, of 25-cent stamps, and Y is the number of 2-cent stamps. So what I can do now, question, how many stamps does he have? He has how many total? 9. How do you get the total number of stamps? Well, you take the number of 25-cent stamps and you add that to the number of 2-cent stamps. There's one equation. But the other one is how much value. Now, for how much value, there's going to be multipliers on there. Now, the first thing I notice here on value is that I have 2 different things running around. I have the unit of a cent, and then I have a unit of $1. You need to get it down into 1 unit, and I will change it all over to cents. You could change it all over to dollars, but then you have to work with decimals in there, and I'd rather work with whole numbers. I'd rather let it be the smaller unit so that the numbers are bigger, and I don't have to work with decimals. So I'm going to do my value in cents. So how many cents do I have total? That's going to be 110 cents, right? Isn't that $1.10? Now, how do I find the value of each stamp? Well, it's 25 times the number of 25 stamps that I've got. And that X does not mean multiplied. The X means the number of 25 stamps that I've got. Plus 2 for the Y's. And then there's my 2 equations. Do you follow? Solve it. Well, okay. Maybe I'll take equation number 1 and I'll solve it for X, and I'll say X is equal to 9 minus Y. And then I'll take that expression and plug it in over here. And I'll say 25 times what X is. What is X? 9 minus Y. Because whatever it is over here, it is over here. Okay, and then plus 2y is equal to 110, and then you can solve it. Solve it for the y variable, and then when you're done, substitute that back into one of the equations, solve for the x, and you're in. Okay. Okay, good. So you need two equations. If you've got two variables, you need at least two equations to get a particular solution. You'll do more about that in pre-calc, but it's something to look forward to now. Okay, now solve the system of equation by elimination. Whew. Let me take a drink here. We're busy tonight, aren't we? All right, elimination. Remember I said substitution was a good way of working with things when you didn't have any fractions. When you look at two different equations and you see on one of your coefficients as a 1, you can easily solve it for that variable and not have to do any kind of fractions. But sometimes you can't. And the elimination method helps you to avoid fractions. Not always, but a lot of times it does. It will here. Solve the system of equations by elimination. Well, if I solve this equation for x, I'd have to divide by 4, which means I'd have to divide that by 4 and divide that by 4. And 32 divided by 4 works, but 6 divided by 4 is a bad idea. That's not an integer. And the same thing for solving it for y. So let's do this. Remember standard form? Standard form said ax plus by is equal to c. And it has to be in that order. But a, b, and c are all whole numbers. They're all integers, and a is positive. So that's another reason why standard form is good. The first equation there is already written in standard form, but the second equation's not. Can I make it standard form? Yes, by subtracting 6y from the right and 6y from the left. And so I get 3x minus 6y is equal to 3. That's equation number 2. Okay, now watch what I do. I'm going to take equation number 2 and bring it over and line it up and stack it underneath equation number 1. 3x minus 6y equals 3. That's equation number 2. Okay? I've got a column of x's, a column of y's, the equal sign, and then a column of constants. Now watch. One of the rules of algebra says if I combine terms properly, I can actually add together equations. So do the column right here. What is a 4x plus a 3x? 7x. Just combine the coefficients. Now, here's where the good stuff happens. What is a positive 6y minus 6y? 0. That's what you want. Equals 32 plus 3, 35. Oh, look! The y's have been eliminated. So that really doesn't exist there, does it, right? Can I solve 7x is equal to 35? Oh my goodness, it's so easy. Divide by 7, this cancels, and I get x is equal to 5. There we go. Okay. Now I want to point something out. Do you see the fraction bar right here, horizontal line? Do you see the fraction bar right there, horizontal line? Good. Some people confuse that with a fraction. This is probably the only time I will let you draw a horizontal line to show addition. It's kind of necessary here. It is what it is. Which is a slight twist on the first law of thought. Whatever is the first law of thought. It is what it is. It's just a little bit different, but they're related. Okay, am I finished yet? No, I've got to solve it for x. Well, which equation do I put, I'm just going to solve it for y. Which equation do I put x in to solve for y? It doesn't matter because x is 5 everywhere. I don't know, let me just do it right here. I got some room to work right there. So it's going to be 3 times 5 minus 6 times y is equal to 3. Okay, 15 is equal to, whoops, not equal, subtract. I'm getting so excited I'm not paying attention too much here. 15 minus, come on, minus 6y is equal to 3. Let me get it out of the way there. And so minus 15 and minus 15, negative 6y is equal to, what's that, negative 12? And then divide by negative 6 and divide by negative 6. So I get y is equal to 2. Bada bing. So final solution, 5, 2. Oh my goodness, yes. Got it. I did it previously. I just double checking myself. Okay. Good. That's elimination. But let's talk why it worked. Remember why it worked? It worked because we got the same number on one variable, but opposite sign. And it just happened that way when we put those two together. They were kind of accidentally that way to begin with. Not really, because I planned it like that. But that's why it works. It works because you're able to get a coefficient of 0 when you add. Sometimes you have to do some work, some algebra, to make the coefficients have the same number but opposite signs. So let's now do the next one. And I think this is the last one, but we'll find out. I lost track. Solve the system of equations by elimination. Notice I'm putting them again side by side rather than up and down. I'm putting them side by side because you have to put them right lined up in the right column, and you got to line them up right. So 2a plus 5b is equal to 6. What? A's and b's? Yeah, it's the same thing as ax plus by is equal to c when we were using x's and y's. When you're doing standard form and you don't have x's and y's, they need to be in alphabetical order from left to right. That's what standard form is. It's alphabetical order from left to right. Okay, so this one's already set up. I'll leave that one alone. How about equation number 2? Well, I got everything on the right side of the equal sign. I just need to swap these two. So I'm going to rewrite this as 2a plus 9b equals 22. Now that's in standard form, and now let me stack them. So I'm going to get 2a plus 9b equals 22. That's equation number 2. Okay, now what? Oh, so close. It looks like the a's can cancel pretty easily there, but they need to have different signs. You could actually cancel the b's if you wanted to, but you'd have to multiply through by something that would make the coefficient on b the same number but the opposite sign for both equations. So that's possible. That's a little more complicated. You can get 45 on the b on top and negative 45 on b on the bottom and then combine them. But we'll do the a's. The a's are a little bit easier. They already have the same number. I'm going to change the bottom one. Here's how I'm going to change it. I'm going to multiply the left and the right by negative 1. And won't that give me the opposite sign on the a term? Yes, it will. Now watch what I do here. I'm not going to draw a solid line. I'm going to draw a ziggity-zag line. That's because I'm altering the equations, but I'm not yet adding them. So I'm going to recopy down equation number 1. 2a plus 5b equals 6. And then I'm going to copy down my new equation number 2. Negative 2a minus 9b, right? Because I have to multiply everything, equals negative 22. Now do I have the same number but an opposite sign? Yes, I do. So I'm going to now add. What's a 2a minus 2a? 0. Oh, that wasn't a good smiley. That's pretty good. What's a 5b minus 9b? Negative 4b, and that's equal to positive 6 and negative 22. When the signs are different, you find the difference. So what's 22 minus 6? Negative, what? Negative 16? Okay, good. Now, divide both sides by negative 4. Divide by negative 4. Cancellations. B is equal to positive 4. Good. Am I finished? No. Maybe I'll come over here and solve it for A. So 2a plus 9 times 4 equals 22. All right, let's run with it. So 2a plus 36 equals 22. So 2a, and if I do then minus 36, 2a is equal to, oh, what's 22 minus 36? I don't have that readily handled. Minus 36. I'm getting negative 14 And then a is equal to then -7. So putting them together, -7 and then 4, because it's a first and then b. I think that works. I'm going to try something. I'm going to pause it for just a minute. All right, I should be back. If it worked right, I paused the video. I wasn't feeling the 4. I thought it should be a -4, but I went back and checked everything, and it's not. Please tell me if you think that should be a -4 on B. But I had the feeling, and I didn't want to stop and bore you with it, so I pressed pause. Don't trust your feelings in math. Sometimes you have a hunch, and maybe the hunch is good, but sometimes it's not. In mathematics, mathematics is not how we feel about the math. Mathematics has to be done through the logic of it. And maybe there's some truth in life that you can get from feelings, and there is. But mathematics is not based on feelings. Mathematics is based upon the logic. So I'm going to go with it. Okay. So -7 for the A and +4 for the B. And now it's down onto the exercises. So I will turn you loose. All right. Should be back to me full screen. Woo! Are you still with it? Man, that's a lot of work. It's good. It's good stuff. Don't be too upset with your difficulties in math. They're frustrating from time to time. Yes, work through it. Don't quit. Don't give up. One of the things that's kind of, I don't know, esoteric about mathematics is every time that you attempt a mathematics problem or try to answer a question mathematically, you are expressing faith and hope that you will be able to come to a conclusion. Sometimes your conclusion is there is no answer, but you're at least certain that there is no answer, like we showed today in the lesson. So it seems kind of strange to say it, but there is an element of faith and hope in mathematics. If there was no guarantee that the truth of mathematics was permanent and repeatable, why would you ever try to use it to solve a problem? Well, it worked in class, but I've got no expectation that it would work when I'm here at home because it's just not a permanent thing. No, it is. Isn't that great? Anyway, it's worth learning. Even if you're never going to use it in your job, it teaches the mind to think and reason and sometimes have patience with hope. So anyway, I hope you have a great day. Talk to you later. Bye-bye.